Okay, good. Good afternoon, everybody, and thank you for joining on today's Grand Round Speakers that is hosted by the Department of Epidemiology and Biostatistics of the CUNY Graduate School of Public Health and Health Policy. At this time, I will turn it over to one of the rising stars of our department, Dr. Zachary Shan, who will introduce our esteemed Grand Round Speaker, Dr. Glymour. Zach, is all yours.
Thanks, Elias. So Dr. Maria Glymour is the chair of the Department of Epidemiology at Boston University School of Public Health. She has done a lot of great work on causal inference methods and also applying these methods to meaningfully address important questions, even when the data are not necessarily as cooperative with causal assumptions as we'd like. And I think relatedly, today, Dr. Glymour will speak about evidence triangulation in research on Alzheimer's disease and related dementias. If you have questions during the talk, please put them in the Q&A, and I'll most likely ask them to Dr. Glymour at the end of the talk, or if they seem pressing, I have permission to interrupt. All right, so thank you, Dr. Glymour, for speaking to us today.
Thank you so much. It's really a pleasure to be here. I'm going to share my screen. Yes, thanks so much, and thanks everyone who's attending. It's great to be here. So I'm going to start by just, as Zach mentioned, my talk is about evidence triangulation and dementia research. These slides were contributed by my student Serena Gutierrez, also contributed to these slides, so I'd like to acknowledge her. She's a PhD student at the University of California, San Francisco, where I was previously, and an outstanding emerging scholar. All right. I want to talk about what is evidence triangulation, just to introduce the concept and kind of why it's particularly important in dementia research. I think it's sometimes not obvious to people that there are particular methodologic challenges related to dementia that make evidence triangulation very helpful. And in fact, an idea that I think has been clear to me that it's been important, and very recently the language has become much more popular around this. I'm going to talk about a few examples from my own research team. I'll talk about these at a pretty high level just to give an idea of how we are approaching using kind of novel methods and gluing together imperfect evidence, as Zach said, to better understand causal structures. One of these is really pretty classic evidence triangulation around the effects of education on dementia. And the others are a little less classical, but I think you'll see the theme here about thinking about what are other explanations for associations besides a particular causal hypothesis. And I'll end with just very briefly some challenges. I want to start by talking about dementia, and I think this audience is probably somewhat familiar with the outcome. It's a pretty important outcome. Probably many of you have worked on it. But there are features of dementia that make it particularly problematic for causal inference. Dementia diagnostic criteria are inconsistent across different criteria. However, there are some common things that you'll find in any criterion for dementia. One is that there's cognitive performance below normal for a population, that the cognitive performance has deteriorated for an individual, that they have had change over time, and that loss induces some functional loss or impairment. So some activity that they like to do or that they value, they're no longer able to do as a result of the cognitive changes. So dementia is more like a disability. It's a functional outcome that can be caused by many different diseases, including Alzheimer's pathophysiologic processes, which we think are sort of characterized by amyloid deposition, cerebrovascular disease, which in the most sort of marked form is considered stroke, and other diseases that or causes of brain injury that lead to impairment. Alzheimer's, so when we say Alzheimer's disease dementia, that refers to the clinical syndrome that arises as a consequence of the AD pathophysiologic process. And it's important to know how cognitive impairment is assessed. It is usually detected and diagnosed through a combination of history taking from the patient and a knowledgeable informant, and an objective assessment, either a bedside mental status exam or more comprehensive neuropsychological testing. So both of these types of information are important for assessments. And cognitive function at any given point in time isn't just a function of disease, of course. Cognitive function as measured at any point in time, even in very old people, reflects a combination of multiple superimposed processes. There's a developmental process that is very active in early life, synaptogenesis, neuronal remodeling. That happens rapidly in early life and slows down, but still occurs throughout life. There are disease processes like what I mentioned, Alzheimer's disease, ischemic injury from cerebrovascular disease, and these kinds of disease processes that cause neuronal injury and death. And then the brain is a living organ and actually incredibly dynamic. So either acute or chronic neural injury is followed by neurologic, cognitive, and behavioral compensation. So you have all three processes kind of co-occurring, so that if you take a snapshot of functioning at any given time, you're seeing the net of those multiple processes. I think the combination of these features of dementia actually basically it's almost like somebody thought up a condition that was really hard to identify causal effects for. There's a long insidious development of disease. We actually don't know precisely how long. That's one of my examples is efforts to understand when the disease changes begin, but it's probably decades. There are multiple likely synergistic disease processes contributing. It is very difficult to measure the onset of disease. It is not an acute onset. There are subtle cognitive, behavioral, and physiologic changes which emerge slowly over the course of the early development. The diagnosis timing, so when you actually get a diagnosis, is influenced by many other characteristics, including co-occurring illnesses, access to care, and educational attainment. So as a result of this, the bias that you would see in a research study based in electronic health records or some other sort of naturalistic clinical setting with passive data collection will be quite different than the bias you would expect in research studies with assessments at designated time points. So if you had a cohort where you went out and assessed people every 2 years, that's going to have a very different bias than if you are using data from electronic health record where people come in for care whenever they're so inclined. There are numerous confounders across the life course, and those confounders are deeply socially patterned. The term IQ is somewhat contested, but whatever you think of as cognitive skills and heterogeneous cognitive skills, as there's no age at which we've measured cognitive skills that we haven't found that it predicts late onset dementia. I think the earliest study that I know of that has a direct cognitive assessment and then follows people up to see about dementia onset is age 11 cognitive skills in the Scottish studies. And at age 11, cognition predicts dementia risk. Life course socioeconomic status, so parental socioeconomic status strongly predicts. It is nearly impossible to be confident that you've measured all confounders. So when you try to think of everything that might influence the risk factors we're interested in and dementia outcomes, it's very difficult to convince yourself from a causal perspective that you've captured all of the confounders. And I once went through some review about all the major risk factors, and basically every single one of them, you can see there's pretty strong prior evidence that it's linked to parental socioeconomic status or childhood cognitive skills, implying that they were strongly confounded. And unless you have a study that has really good prospective measurement, covariate control is going to be challenging. I want to turn now, with that context for dementia, I want to turn to the question of what is evidence triangulation. I think the really nice recent articulation of this was from Debbie Lawler's paper, in which she says, evidence triangulation is strengthening causal inferences by integrating results from several different approaches, where each approach has different and assumed to be largely unrelated key sources of bias. I think that is a perfect statement of the intuition. I really like that paper. I think that the vision of evidence triangulation is a little bit broader than what she kind of laid out there, but I think it's incredibly useful paper and gets to the heart of evidence triangulation. Jeremy Lebruck and Sonia Swanson, in a very nice recent paper, have tried to be slightly more formal than that intuition about finding unrelated biases. And they've given this definition, which I think is also a little bit too narrow, but is incredibly helpful to think about what this means formally. So this is from Lebruck and Swanson. If we have evidence triangulation is when you have multiple estimators, such that if you apply both estimators to the same data and research question, you would expect them to agree when the causal assumptions are satisfied for both methods. And you must compare estimators that, given substantive knowledge, are expected to agree only when they are both unbiased. In other words, that you expect the biases to go in different directions. I thought that was really helpful clarification. Is evidence triangulation new? Of course not. This is kind of the essence of scientific thinking in some sense. Like you can go back to sort of scientific reasoning, depends on this idea of evidence triangulation. And this is from Bradford Hill's some of his famous work, because the idea, I think if you reread that, the idea of evidence triangulation sounds a whole lot like what was meant in the Hill criterion by the idea of consistency. Now, this is totally different than the way we use consistency in causal inference language now. But he said, the consistency of the observed association has been repeatedly observed by different persons in different places, circumstances, and times. The lesson here is that broadly the same answer has been reached in quite a wide variety of situations and techniques. In other words, we can justifiably infer that the association is not due to some constant error or fallacy that permeates every inquiry. And we have indeed to be on our guards against that. The same results from precisely the same form of inquiry will not invariably greatly strengthen the original evidence. I would myself put a good deal of weight upon similar results reached in quite different ways. I really love this quote because I think we, as a field, we have not put enough emphasis on trying to juxtapose studies with different weaknesses. We've been much more emphasizing like not having weaknesses or avoiding weaknesses, but I think that's sort of a lost cause. Almost every study has important limitations. So the key is to think about what are the most important limitations and how can I design a different study with different limitations. And I think that's, as I said, familiar to many scientific processes. I actually think this is a version of the evidence pyramid, which was sort of, I think when I was training, was presented fairly uncritically. And now I think we really are starting to see a lot of the limitations. So variations on single methodology have long predominated in observational health research. Modern causal inference frameworks actually, people think about modern causal inference methods as being, marginal structural models or IPW or something, but actually, I think one of the most valuable take-homes from modern causal inference frameworks is we can be very specific about the assumptions we need to identify the effects we're interested in. So by sort of laying out what those assumptions are, it helps us say, oh, that assumption is very questionable in this study design. Can we find another study design where it's better addressed? I think more and better data and computational power offer more opportunities for us to rule out inconsistencies that might be due to chance. And the evidence pyramid and dominance of the particular study design, and I'll go into more about what that is, but roughly speaking, when I say the study design that has dominated, I mean studies which are essentially measure the exposure, follow people up for a while, see if the exposure predicts the outcome, controlling for a set of covariates that you hope capture all of the common causes of the exposure and outcome. In causal inference language, backdoor criterion-based methods. So the evidence pyramid and the dominance of that particular study design has led, I think, to an oversimplification of causal inferences from the field as a whole. And the assumption that as we climb the ladder to the best possible research design, basically an RCT, we can then draw inferences from the design using meta-analysis. Increasingly, we see limitations to that framework, because in fact, you can't just assume that if you go from case control to cohort and from cohort to randomized control studies, every study at a higher level is addressing the key weaknesses of the study design below it. In fact, you have to be a little bit more systematic about what the actual important weaknesses are in each study. So replication without triangulation does not necessarily strengthen the evidence. And this has been an important limitation in dementia research in particular, but I think elsewhere in epidemiology as well. I want to mention meta-analyses because I think of evidence triangulation as a framework for evidence integration and synthesis, and that's really, meta-analyses are probably the predominant tool in our field to integrate evidence. But meta-analyses are really intended to combine estimates from similar studies. By combining estimates, they make chance an increasingly less plausible explanation for findings, so you can get better and better confidence intervals. But if all of the contributing studies rely on the same assumption, then the meta-analyzed result also relies on that assumption. It really has not solved your problems at all. So our dominant tool for evidence integration actually kind of explicitly avoids evidence triangulation. All right, so I want to talk just very briefly about causal inference frameworks here, because I think it's helpful to have, I assume this audience, most people have directed acyclic graphs in the back of your mind when I talk about methods. When we think about causal inference, there are a gazillion specific statistical approaches, but almost all of the approaches for causal inference can be put into one of three buckets. The first bucket, as I mentioned, is blocking all backdoor paths. That is, if you are interested in the effect of X on Y, you identify everything that influences every path that goes into X and also into Y. So it's a backdoor path connecting X and Y. And you've blocked that path, for example, by controlling for a confounder. I will generally refer to these methods as covariate control methods, because I think that that is a little bit more, connects a little bit more easily to people who are not in the causal inference. Like the backdoor criterion is a little causal inference lingo, but everybody knows this method. We just control for covariates. But the key assumption here is that we've captured all of those paths from common causes of the exposure and the outcome. The second, and tons of specific methods really rely on the backdoor criterion. The second big bucket of approach is to use an instrumental variable. And for epidemiologists, of course, the most common and dominant instrumental variable is the randomized controlled trial, where randomization is an instrument for the treatment received. But of course, there are also quasi-experimental and natural experimental approaches that'll deliver instrumental variables. And I want to emphasize here that I'm not just saying doing an IV analysis where we derive an IV effect estimate, for example, using two-stage least squares. I'm really talking about the idea that we are interested in estimating the effect of X on Y, or even just testing that there is an effect of X on Y, and we use some third variable that influences X. The key structure for an instrumental variable is just like with a randomized trial, where we have some source of random variation in X. That says Z in this DAG is that source of random variation, and that's called the instrument. And that source of random variation influences the exposure. It has no direct influence on the outcome except via the exposure, and there are no common causes of that instrument and the outcome. So essentially, all the assumptions of a randomized control trial, of a good randomized control trial, you need for instrumental variables, whether those are from randomized data or from natural experiments. And the third bucket is the front door criterion. I will not spend any time talking about the front door criterion, but if somebody wants to ask me about it in Q&A, I'd be delighted to talk about it. It just is still not widely used because the assumptions are strong and most people can't find settings where they think it's viable. But I haven't given up hope. Somebody might find one. Maybe somebody in this audience will be excited about the front door criterion. So observational health research has been dominated by methods that rely on this first of these options, fulfilling the backdoor criterion. I will note that economists tend to rely much more heavily on instrumental variables. So if you read econ journals, they're much more dominated by IVs or other types of natural experiments. Dementia research is very much dominated by backdoor criterion approaches or covariate control approaches. So the Lancet issued a really very ambitious review of causes of or opportunities for dementia prevention. And they suggested that perhaps 40% of the cases of dementia could be prevented by interventions across the life course. I kind of love this study for the fact that it has made this picture, which almost everybody in dementia complains about this picture, but this picture conveys the concept of population attributable fractions and life course in a way that I think was previously unfamiliar to many people in dementia research. So this picture just conveys interventions at different life course periods, early life, midlife, late life, and the population attributable fraction associated with each risk factor. But when you actually drill down into this report, almost all of the evidence is based on observational covariate control examples. So Livingston sort of argues, oh, we've got strength, consistency, biological plausibility, temporality, dose response, coherence, and quasi-experimental studies. But in fact, the number of quasi-experimental studies or the number of studies that use any variation on the core approach are quite limited. And in fact, in some sense, in some cases, it's very hard to believe that the backdoor criterion has been fulfilled. And further, I think researchers are actually nervous about this. So my example to illustrate kind of how cautious we are, how unsure we are of our research in dementia is alcohol use in dementia. Alcohol use is a really important risk factor because it's very common. And so if it has even modest harms or benefits, it could be an important influence. In fact, very commonly in observational studies, and in fact, I believe in the meta-analyzed results in Livingston, the group with the lowest dementia risk are the people who have light to moderate drinking. But in fact, the recommendations are against heavy drinking, but they're not in favor of light to moderate drinking because nobody's quite comfortable that the methods are good enough to really rely on recommending something that we think may have adverse public health effects. So ultimately, because we're so cautious about them, so unsure of these methods, as we should be, we end up only making recommendations for things that we already thought were a good idea. This is not really that useful as a scientific approach to say, oh, this thing that everybody already wanted to do is probably good. If we want to really be willing to make recommendations that actually give new insights and new advice to people, or new recommendations for policy, we really need to strengthen our approaches to identifying causal effects. All right, I want to talk now about some specific approaches to evidence triangulation, and then I'll jump into some of the applications. Are there any questions so far, Zach, that I should stop and try to address before I?
No, not yet.
Okay, I'll just keep going. All right, so I'm going to talk about these approaches, and I think it's helpful to contrast them against a conventional study, where the conventional study is a backdoor criterion approach where we've controlled for covariates. So multivariable regression, propensity score modeling, stratification, inverse probability weights, all these various statistical models, whatever was used to control for confounders. And then looking at, for example, incident dementia. So that's the classic approach. So imagine you have such a study and now you want to strengthen the evidence. So what are some approaches to do that? So one approach is a meta-analysis or a meta-regression. And as I mentioned before, the meta-analysis, this is just a picture of the meta-analysis, one of the meta-analyses presented in the Lancet report. Meta-analyses are very helpful to combine multiple studies with similar designs and measures. They're great for that. However, they really help rule out chance, right? But they cannot address the fact that if the underlying studies didn't control for confounders, then the meta-analyzed result also doesn't control for confounders. Meta-regressions, where you do a meta-analysis and then you use features of the contributing studies to, you stratify by features of the contributing studies to look at effect estimates within different types of studies or studies with different characteristics. I think that actually can be quite helpful for evidence triangulation and identify research settings in which the association really differs. And I think that is that can be a very useful approach. Another approach to sort of complementing conventional methods, and I think this is so clever. And if you are working in a setting where you have an opportunity to do this, I think it's really great, which is cross-context comparisons. And the idea is so here's the DAG, you have a setting where you think X and Y are confounded by U1 and another setting where you think X and Y are confounded by something else, ideally even in a different direction. And then you can see if the association between X and Y is similar across these settings. So the idea is comparing associations of exposure and outcome between populations or the same population at different times with different confounding structures. For example, exposures that are indicative of social advantage in one setting, but social disadvantage in the other. I think one of the loveliest examples of this was around breastfeeding and infant development. And the comparison was in Western countries where breastfeeding was at that time really associated with socioeconomic advantage, and a South American country in which the reverse was true. The breastfeeding was really associated with social disadvantage. And showing that the effect estimates were actually pretty similar across these two very different settings where the confounding structure would be totally different it's a very powerful approach. This is also a real argument for doing cross-national studies, for doing work in diverse settings. Another important complementary approach, which I think has driven a lot of the recent discussion is an interest in instrumental variables analysis. So of course, the randomized controlled trials are great. For dementia prevention, they're not that feasible. It's hard to do a randomized controlled trial for prevention because it's so slow. There's been a lot of interest in instrumental variables using genetic variants. And this is using one or more genetic variants that influence the exposure of interest, and then evaluating whether those variants also influence the outcome of interest, presumably via the exposure of interest. There are lots of caveats to genetic IV. I actually think it's often very helpful. And in particular, I will say that when I first heard about genetic IV, I was a total non-believer. Like I was absolutely a skeptic. And I've really come around to some of the uses of it because the things I thought would go wrong were not what goes wrong. Like I thought, oh, you'll see everything is associated with the genetic variants, but actually that's not the case. It's very hard to find a genetic variant with a strong enough effect on any exposure. And I think I'll show some examples of using reverse MR, which I think are helpful. But of course, genetic variants are not the only source of variation. And although the term MR was coined only 24 years ago, the idea of instrumental variables is more like a century old and has been used very widely for use based on policy variations, sort of arbitrarily timed changes in policies, systems rules that essentially have arbitrary discontinuities in who gets a resource or who doesn't. I think there's a whole set of really cool instrumental variables now that are based on judges or people who make decisions for about a distribution of a resource, or and because some judges are generous and some judges are not generous, you can basically use that as a natural experiment for the effects of the resource. Another approach is, or another category of approaches is bias demonstration and quantification. I think these are often quite helpful. Negative control, either exposure or outcome controls. The idea here is that there's similar conditions as the primary study. You find a study with similar conditions, but use a different variable with a well-established null association, either conceptually or scientific or empirically, you know that this exposure has no actual effect. However, it should have a similar confounding structure. And I'll briefly talk about an example we used. Evaluation of reverse causation. So that aims to establish the potential for reverse causation from the outcome to the exposure. I think this is really helpful for dementia because there's so much reverse causation because dementia begins so early. And quantitative bias analysis, I think this has become much more popular now. These computational tools are fantastic to really try to write down like, okay, how big would the bias have to be? I think the very simplest types of formulas like E-values are helpful to think about. And then you can use that to sort of say, okay, let's really try to figure out how big the bias is. I think one of the biggest challenges with DAGs, with directed acyclic graphs, is because they are non-parametric. It's easy to see biases and it's hard to see it if it's an important bias or it's like a small thing that is not really going to give you the wrong answer in any meaningful sense. So I think QBA can be a very helpful complement when you're using DAGs. All right, so that's the sort of background on evidence triangulation, why it's important for dementia research and some of the approaches. And now I'm going to talk about some specific examples from my group that we've been pursuing over the last few years. The first example focuses on the question of whether educational attainment, prevents dementia or delays the onset of dementia. I will say there is a lot of observational evidence suggesting that education reduces dementia, that people with more education have lower dementia incidence. This is a picture from one of several meta-analyses suggesting that high education roughly cuts dementia incidence in half. Nearly all of these studies share the assumption of no confounding by prior cognition or parental socioeconomic status. It's very hard to believe that access to education is not related to prior cognition or parental socioeconomic status. So I was very skeptical of these results. However, we actually have an amazing natural experiment that happened in the United States and in fact, in much of the world over the last century. There were rapid increases in mandatory schooling in US states. And these rapid increases in mandatory schooling, like increases in the age when how old somebody had to be before they could drop out of high school, or how old they had to be before they could get a work permit. That's what I mean by an increase in mandatory schooling. But those increases led to rapid increases in educational attainment. This on the left is a picture from Claudia Golden's work. She did really important work on the high school revolution in the United States. And it just shows how rapidly from the early 1900s through the mid 1900s, how rapidly we got most people through, I should say most white students through high school. We moved from being a country where it was quite rare for children to complete high school to being where it was the norm for white children to complete high school. After sort of in the second half of the 20th century, we started increasing access to schooling for Black and Brown students. And if you plotted this, you'd see similar rapid changes for more diverse student bodies. This on the right just shows you just an example of kind of how this setup is. So on the x-axis here is the birth cohort. And for each birth cohort, you can calculate the mandatory compulsory schooling. So the laws that were in force at age 6, when they said you have to go to school at age 6 or age 7 or age 8, and the laws that were in force about what age they could drop out. And you can see that for children born in like 1925, they were required to go to 6 years of school. But children born a year later were required to go to 8 years of school. And then in 1934, they changed the law again, adding another year. So basically, whether you're born before or after that sudden change changes the minimum legal mandate for schooling. And this has been shown repeatedly actually did increase schooling. Not everyone drops out the second it's legal to. In fact, most people don't drop out the second it's legal to drop out. So it's not like adding 2 years of mandatory schooling adds 2 years to average educational attainment. But a substantial fraction of like 10% of children basically are constrained by these policies. So you can see it in large data sets. This is work led by Tu Nguyen, who is now on faculty at the University of Maryland. And this is Tu's little one. But we have several sort of complementary studies, but I think this is a really nice illustration because she compared within the health and retirement study the estimated effect of education on dementia risk using a confounder control approach, where she found, if you just control for covariates, you get an estimate of each additional year of schooling reduces cumulative incidence of dementia by 2.1 percentage points. If you use a genetic risk score for education, so you can actually create a genetic risk score for education, you see an association of around 1 percentage point, also protective. And if you use the compulsory schooling laws, you see an association of about 9.5 percentage points, really large, but also protective. And this kind of pattern, so consistent across all of our approaches, the magnitude of the effect varies. Subsequent research has largely replicated these findings in diverse data sets and addressed some of the key confounders in covariate control. So for example, there's a really nice study coming out of Wisconsin longitudinal study where they could control for high school cognitive scores. A similar really lovely research led by Marilyn Thomas in the Project Talent data also had early life cognition to control for and found very similar patterns. Questions remain, I think, very important questions about the possibility that education makes it harder to diagnose dementia, but does not affect the underlying disease and consistency of patterns. So the idea that if you have more education, it's harder for a neurologist to actually say, okay, this person has dementia, and they get you later in the disease. They can't tell until you're later on in the disease process, which would of course look like it was protective, even though it wasn't really changing your life. I think another set of important questions are the consistency of educational protection across different social settings. So for example, we believe that when Black students started to get more access to education, Black men encountered much more structural discrimination in the labor market than Black women. And so the racism in the labor market targeting Black men made it much harder for Black men to sort of reap the financial benefits of extra education. So in that kind of setting, and of course there are many settings where people are sort of structurally blocked from using education in the ways that we might hope. And so there's a question of, does education help people what's the payoff in terms of health when you're in those kinds of settings? All right, that's my first example. The second example, and this is a little different, but I think also really interesting set of projects to try to understand at what age do dementia-related diseases begin to change physiology and phenotypes. And this is work, lots of folks have contributed to this work. Willa Brenowitz, who is a scientist at Kaiser in Portland, and Scott Zimmerman, who's a senior research analyst in my group, Peter Buteau and Min Choi, who are both analysts, wonderful analysts in my group, have all sort of contributed to this set of interlocking papers and extensions we're doing now. So why is this question important? It's important because we have to understand when a disease begins to understand when prevention has to occur. You can't say we're going to do primary prevention when you don't even know when the disease begins. It also is important to help us understand if interventions are failing because we're starting too late. That's a common response, but actually it's a little unclear. If you're interested in identifying determinants of dementia, then it's important to understand reverse causation because that drives the potential for confounding of time-varying risk factors such as BMI and hypertension. It also, I think, is important for understanding whether amyloid is a leading indicator of disease. This is a whole debate related to medications right now, which are premised on the assumption that amyloid is the key biological driver of disease. Okay. So this is actually really hard to figure out because the disease is so long and slow. And just to give you an example, we started with body mass index. So midlife obesity is a risk factor associated with increased risk of dementia in late life. It's pretty well established. It's also pretty well established that people around the time of diagnosis of dementia or Alzheimer's disease, that they often have weight loss. That typically that diagnosis is associated with weight loss. It's a little unclear why it's associated with weight loss, but it's pretty well established. So we asked, when does dementia-related weight loss begin? Like at what age is dementia-related weight loss detectable? But you can see these two things are going in the opposite direction. So it may be really difficult with typical methods to figure this out, to figure out the association. So our idea here was to use a genetic instrument for Alzheimer's disease. So use the genetic instrument that influences Alzheimer's disease and see when that genetic instrument begins to be associated with body mass index. So just to draw out the DAGs, if we are looking in the top DAG, if we are looking at a period in life when there's no, like preclinical dementia has not begun to influence weight loss, the genetic risk score for Alzheimer's disease may influence preclinical dementia, but it won't be associated with weight loss. It's deseparated from weight loss because this hasn't started yet. Whereas if there's already an influence of preclinical dementia on weight loss, we would expect the Alzheimer's disease genetic risk to predict weight loss. And so we kind of conceptually what we want to do is see at what age does the Alzheimer's genetic risk become associated with weight loss. We use the UK Biobank for this. This study design really requires a very large sample. So the main advantage of the UK Biobank is it's about 400,000 people, ages 40 to 69 at baseline. We created an Alzheimer's disease genetic risk score and measured BMI at study enrollment, and then estimated a linear regression of BMI on age squared, and interactions with ADGRS. And the idea here is to let ADGRS, basically the effect of ADGRS on BMI, emerge as among older people. And we've kind of, the first work we did use this linear regression approach. In a more recent approach, we have a more complicated setup where we first look to see if there's any interaction between the ADGRS and age. And then we have a segmented spline, and we basically choose the age of the best fitting age of divergence for that interaction. And I'll show you a little bit more. But right now, the first thing I'm going to show you is the linear regression of BMI on age squared, and then predict out curves of BMI for people with 10th and 90th percentile of Alzheimer's disease risk. So this is actually the picture, which I think is the most compelling explanation of this approach. So if you see there in red is the predicted BMI for people with low Alzheimer's risk, and in black is the predicted BMI for people with high Alzheimer's risk. And what you can see is, you know, at the beginning, at the earliest, now remember, this is cross-sectional data. So these are comparing people who are 40 to 41, 44 to 45, et cetera. But at the beginning, there's really no age-related difference in BMI. I mean, there's no there's no difference in BMI based on the AD genetic risk. The AD genetic risk is just unrelated to BMI for people down in their early 40s and even mid 40s. Somewhere here in their late 40s and clearly by mid 50s, that diverges, and that people with high genetic risk for Alzheimer's disease begin to lose weight more quickly. And so that to us is suggesting there's something happening physiologically quite early here by roughly age 50. We extended that approach to cognitive assessments and neuroimaging measures. You might think cognitive assessments would be the natural place to start, but we start with BMI. And the way that we did this was we searched across all variations of cognitive assessments that were available in the UK Biobank. This sample in UK Biobank, this cognitive measures are a little inconsistent across individuals. We then used Bonferroni corrected thresholds to identify cognitive measures with a significant age by genetic risk or interaction. And then for those with an interaction, we chose the best fitting age of divergence using the threshold for age when ADGRS becomes relevant. So the coefficient for the ADGRS is held to 0 prior to that age, and then it's allowed to fit and grow the difference after that age. And we just looked across every possible age and chose the best fitting. And when you look at this actually, so this is a summary of a lot of results. So from age 40 to age 82 is the average age of dementia diagnosis in the UK. This is our best estimate of the age of divergence for these cognitive outcomes. So PM is like pairs matching, SD is symbol digit substitution. And it doesn't matter so much the specific tests, except to say, it really is looking like some of these, there's divergence in people's late 40s. These that suggest divergence prior to the earliest point of the study, we take with a grain of salt because we don't actually have data on that. We're just extrapolating. But for these starting in the early 40s, you know, the youngest people, it doesn't look like the ADGRS is related to these cognitive measures. And as people get into middle age, the ADGRS is associated. And then you can actually, with the neuroimaging measures, UK Biobank has about 50,000 brain MRIs. And you can do these plots to look at the best age of divergence by various neuroimaging features. And you can see, although some things really, the ADGRS isn't relevant until people are in their 60s, 70s, and 80s. Some things, they become relevant in people's 50s. Nucleus accumbens, hippocampus, amygdala. All right, so conclusions from example 2. At what age do dementia-related diseases begin to influence physiology? This really suggests that Alzheimer's disease-related changes in BMI, cognition, and brain MRI measures begin to emerge in people's when they're in their late 40s to early 50s. There are some important caveats. This is a strange sample. The UK Biobank has a very odd selection process. It's very, very high SCS, very healthy, and they were very cognitively healthy at baseline. The analysis I just showed you is really cross-sectional, not longitudinal, because they don't have longitudinal cognitive changes. And the changes could be attributable to pleiotropic effects of genetic variants. I will say our biggest concern when we started this, when we published these, was the UK Biobank sampling weirdness. We're just starting to do this in All of Us and in the All of Us cohort, and which is just getting old enough to use for dementia work. And so for BMI, the results are looking pretty, like they're holding up pretty well in All of Us. So that's quite reassuring, but that we're at very early stages there. The implications here are that Alzheimer's disease research, if we begin at age 65, is at least 20 years too late for primary prevention. Risk factor associations for measures in middle age or later are potentially confounded by emerging diseases. So I think the implications here can be pretty important. All right, moving on to example 3. This is a set of papers around the question of whether factors that cause cancer might also reduce the rate of dementia. There are several studies that suggest cancer survivors have lower incidence rates. And by incidence rates, I mean cases per unit time, not cumulative incidence across your life. But if you're alive at a given moment, what's the probability that you develop dementia in that period? If you have a history of cancer versus if you don't have a history of cancer. So there's several studies suggesting lower incidence rates of dementia among people who are the same age associated with having had cancer in the past. There's an obvious explanation, which when I first read this observational result, I snorted and said it's obviously selective survival. That is inconsistent with several lines of evidence, including the fact that this observation is seen with non-fatal cancers. So the obvious simple explanation is not adequate. And I want to emphasize, we're not necessarily arguing here that cancer might reduce risk of dementia. We're arguing that there's a shared biological process, one of which causes uncontrolled cell growth, as in cancer, and one of which, and the same process may reduce the chances of inappropriate cell death, as in dementia. So, and this is pretty interesting in terms of understanding the biology of dementia. So we tackled this. This is a bunch of people worked on this project. We basically have wrapped up this grant just about. But this is work led by Monica Espino-Romero, who's a neuropathologist at Wisconsin now, Lindsay Kobayashi, who's on faculty at the University of Michigan, Jingshuan Wang, another amazing PhD student at UCSF, Elizabeth Rose Maeda, who's on faculty at UCLA, and Eleanor Hayes-Larson, who is a postdoc working with Elizabeth Rose until, I think, for another 2 months. She's a postdoc, and then she'll be on faculty at USC. So these, I'm just going to talk about these different projects. Monica and Lindsay began by doing a meta-analysis in which they really systematically stratified the studies by the type of bias and looked at how the results differed across studies based on the type of bias. I'll show you their key results. They also did a negative control study where the negative control was the spouse's rate of memory decline. So if there's a shared biological process that influences cancer and dementia, your spouse's cancer should not have an effect. And in fact, what they found was that there wasn't really an effect on the spouse's cancer, although there was, they saw the same pattern if you're on your own cancer, but not in your spouse's cancer. And Elizabeth Rose and her team, Eleanor Hayes-Larson, did wonderful quantitative bias analysis, trying to sort of say, okay, let's try to write down a model that would explain this. And finally, Jingshuan looked at bias due to diagnostic bias in the UK Biobank. And so here's kind of the setup of the approaches and how they added to the core evidence. So the meta-analysis and meta-regression, the log hazard ratio, excluding studies that had each type of bias, ranged from -0.09, so like a 10% protection, to -0.3, so about a 30-35% protection. The key upward bias, i.e. Studies that made cancer look less protective, was due to studies when cancer status might influence AD diagnosis. So if you got cancer, you're going to get more healthcare. And that increases the chance you'll be diagnosed. The key downward bias, i.e. things that made cancer look more protective, were bias from survival. So if prevalent and incident cancers were combined. The next approach was this negative control using spousal rate of memory decline, and they found almost no association among the negative controls. The next approach was bias quantification, and I think the simulations actually showed, the simulations were really based on real data, so we could parameterize them pretty well, and then say how strong or what kinds of interactions would we need to explain the patterns with competing risk or selective survival. And I think the classic versions of those really couldn't explain the observed cancer dementia association. What did matter was the possibility that there's a delay between when you develop dementia and when it's diagnosed. And some people die during that period between when they have cognitive impairment and when they're actually diagnosed with it. And that is an important potential bias. So if you have substantial mortality between onset of dementia and diagnosis of dementia, and that mortality is higher among people with cancer, you can quickly induce a bias. So their bias quantification really highlighted the thing we have to worry about. And then Jingshuan's work, where he actually looked in electronic health record data sets, and this was largely in UK Biobank, showing a very large increase in dementia hazard in the first year after cancer diagnosis, an 80 to 120% increase. And this really, as we drill down, we really think this is about diagnostic bias, that if you go into the physician, if you have an older adult who's kind of been doing their thing, maybe having a little bit of cognitive impairment, and then they get screened for cancer and diagnosed with cancer, and suddenly they're having a lot more engagement with the healthcare system, they're much more likely to be diagnosed with dementia. This is Monica's paper. I won't spend much time on it, except to say you can see how she sort of grouped things as bias from how confounders were handled, subject to bias from diagnostic bias, subject to competing risks bias, subject to survival bias, missing data issues, and looked at the coefficient across each of these sort of buckets to see how much, if you could get a really substantively different answer across these different approaches. All right, so conclusions from this group of papers: do factors that cause cancer reduce the incidence rate of dementia? I would say that my opinion is maybe. It seems like a plausible story, but we could not possibly evaluate that using data from electronic health records. We really need very different data sources because the bias from healthcare utilization is so substantial. All right, my last example is focused on evaluating medications with a shared biological mechanism using instrumental variables. This is work really led and championed by Sarah Ackley, who is a postdoc with me for another few months, and then will take a faculty position at Brown. So this work is really responding to, it started actually before we're in a sort of different era now. It started probably 5 years ago. And at that time, there were a lot of drug trials targeting amyloid burden in the brain with the goal of developing medications, monoclonal antibodies that would remove amyloid from the brain as a way to treat dementia or prevent the development of dementia among people who were sort of on that pathway. And there were all these drugs, and a lot of them had null results. There were all these trials, a lot of them had null results. And the idea was, well, can we meta-analyze them to get an overall effect estimate? Well, you can't directly meta-analyze them because the different drugs had different effects on amyloid, right? So if you directly meta-analyze them, you get some gamish. But they all had the same idea, like in theory, they had the same biological pathway. So the idea was we could use an instrumental variable analysis to get an estimate of the effect of amyloid reduction on cognitive outcomes, and then meta-analyze the IV estimate. Many studies, now we don't have the individual level data, the companies are not that excited about sharing it with us. Many studies reported grouped data across multiple randomization arms. Often there were multiple doses. So there's like the no treatment and then different doses of drug, each of which would have a different effect on amyloid removal. And then a cognitive measure. And very often they measured amyloid, the key biomarker, endogenous variable in the IV. They would measure that just on a subgroup of people because it's so expensive to measure. And this was a little bit of a non-traditional IV because we have only grouped data and we have uneven sample sizes. But Sarah did a really nice job tackling that. Here is the DAG again, where you have people randomized to various drug doses ranging from 0 to the high dose. There's amyloid reduction is what we're really interested in as an exposure, and cognitive outcomes. And these on the left is Sarah's first paper looking at this, which she published in BMJ, along with a sort of methods primer about the idea. And each trial, you can see there's an IV effect estimate for each trial. And you can see there's a lot of heterogeneity in how informative each trial is. After she published this, about 4 trials were published late fall of 2022. And some of them showed significant cognitive benefit, some of them did not. So she updated this study. And there was tremendous disagreement in the field at the time about what really was going on. So she said, let's do a Bayesian analysis, assuming different priors. So we can take a prior that's exactly her prior meta-analysis, right? So that was the effect estimate from the meta-analysis. We can take a prior that's like, you think that there's publication bias, there's actually nothing. There's no effect at all. So that's a prior. We use the same width as we got from the meta-analysis because we didn't think you should be more confident than all previous studies. You could have a prior that there was putative harm, again with the same width, but like a substantial harm, or a prior based on the most optimistic prior study. And here's the posterior once you integrated all the new studies. And what you can see here is the posteriors are really similar. It actually doesn't really matter where you started. The new studies had so much more data in them that you ended up in really similar places, saying there is probably a small cognitive benefit of this medication. And it's probably not large. You can see the upper end of this confidence interval is not large. But there is some small cognitive benefit. And that was really nice because like graduate 1 and 2 actually didn't find significant effects within the studies. I believe that's right. Gantenerumab, but there's no statistical evidence that they were different. Actually, they just didn't have as much power because they didn't reduce amyloid as much. So this approach, evaluating medications with shared biological mechanisms using instrumental variables, there are some caveats here regarding biological heterogeneity of the underlying amyloid species. That has been a huge, there's been a lot of interest in explaining divergent results across drugs with that. However, there's actually no clear statistical evidence that the drugs have different effects based on the species that they target. It's just that they have different success in removing amyloid. Of course, the confidence intervals are wide, so there still could be heterogeneity. There are other challenges in the IV due to aggregated data. It would be great if we actually had individual level data, and many of the trials never published data, so we couldn't do anything with them. But this seems like generally a straightforward complement to standalone trial data and really valuable to temper interpretation of chance results from single trials. All right, I am almost done. I want to just talk a little bit about some of the challenges. One huge challenge I have found in integrating findings has been, how do you actually combine results? And I think what's happening in the field is these very kind of casual reviews to say, this was beneficial, this was beneficial, this was beneficial. And, or just a conclusion that like the observational evidence says it's protective, the trial said it wasn't, the trial must be right. But I think that in fact, we have to be much more systematic about how we integrate evidence across studies. And that means saying, are these the same? Are these identifying the same causal estimands? Is there the same exposure definition? Is there the same outcome definition? This comes up a lot in Alzheimer's, where I think a very important problem is many studies are looking at cognitive change and many studies are looking at incident dementia. These things should be interpreted together, but we don't have great tools to do that. Are there true differences between populations? I think the new transport methods are fantastic and very promising to address this. And we need to ask all these questions before we combine results. And likewise, identify likely sources of bias and use bias analysis to correct them. In conclusion, interest in evidence triangulation is growing, but we still really need a sea change in enthusiasm for finding out we are wrong. Like evidence triangulation depends on people being willing to say, this is a key weakness in my study, and I hope somebody else can try to, poke a hole in it or show that it's okay. Computational tools and data resources for evidence triangulation are growing. And I think honest statements of sources of uncertainty are really essential for progress. I want to end by thanking my amazing group. And this is a group I'm always behind updating these pictures because people graduate and go off and do wonderful things, and I'm always behind on this. And National Institute on Aging for funding. The Advanced Psychometric Methods in Cognitive Aging workshop is just fantastic. Melodem, if people are interested in dementia and research methods, Melodem is really fun. And several grants. This is the slide for Melodem, which is basically just a working group around methods focused on dementia, issues around dementia. And I will stop there. Thank you. And maybe we'll have questions now.
All right, thanks a lot. That was a great talk, really thought-provoking. First, maybe do you want to just talk about the front door criterion, like you like you said you might want to? Yeah, any like tempting front door criterion study designs in dementia, or reasons why it's hard to come up with them? Or
well, okay, and I'm really not an expert in front door criterion. So the front door criterion, for people who are not familiar, which I assume is most people, is the front door criterion. The assumption is that if you have an exposure and outcome that are vulnerable to confounding, so there's a common cause that you didn't measure that influences the exposure and the outcome, but you have measured every mediating pathway. You have a measure on every mediating pathway between the exposure and the outcome, and the mediators have no direct confounders with the outcome. So there's no confounder that influences both the mediator and the outcome. In this case, you can actually identify the total causal effect of exposure on outcome. And it's really hard to think of settings where you believe that. That said, if you talk to people who are unfamiliar with IV, they'll say, oh, you'll never fulfill the IV assumptions. And I believe, like, if you talk to economists, they'll say you never fulfill the backdoor criterion assumptions. So I think there really is some promise for this. And Judea Pearl says, and I can't remember who's actually done the primary work, that the method is actually not that vulnerable to, like, it's not that sensitive to violations of the assumption, that you can still get about the right answer even if you have violations. And I haven't tried like simulations to actually convince myself that that's true. If anybody else has, I'd love to hear it. But because I think this does come up a lot, that it would be really helpful, but I've never found a case where I'm like, yeah, that's a front door criterion setting.
Same. So okay. There is a question in the chat. How can findings from evidence triangulation in dementia research inform clinical practice and policymaking?
Yeah. I mean, I really think we need to be much more. Okay, so one thing I think is a lot of epi and health research, especially with social epi, is kind of disregarded because people don't believe the methods. And I think economists are often much more influential in policymaking settings, and they systematically do not believe backdoor criterion-based approaches. I mean, it's not that they never believe them, but they are very skeptical. And so I think using evidence triangulation could vastly improve our relevance in terms of convincing people that we are getting the right answer. And also convincing people that we would be able to acknowledge it and learn if we got the wrong answer. And I think the same issues are true for clinical practice. Like, in clinical practice, we have some view that the gold standard evidence is randomized trials, but they're so limited and inflexible what there's so many clinical decisions that have to be made without randomized controlled trial evidence. So now there's tremendous interest in using real world evidence. Well, real world evidence basically is backdoor criterion, in most iterations is backdoor criterion. So I think it would be incredibly helpful to try to complement that with IV methods. I think my personal view is that healthcare systems are just like huge little seething pots of natural experiments, because people are always doing things kind of arbitrarily because they're just complicated systems. They have a whole bunch of rules, and the rules are not necessarily based on anything. They're just the rules that have always been the rules, or they're the rules because the clinician trained at a place that did it this way versus that way. And so there actually is a lot of potential for natural experiments that we are not using very well. Yeah. Let's see.
That leads in nicely to the next question, which is whether there's any research regarding drug use or policy change as an instrument. I mean, you gave the example of mandatory schooling as policy change, but any other policies and drugs that might be?
Well, okay. So in terms of the other quasi-experimental areas, like, I think there are actually a lot of unused opportunities in dementia research. So alcohol taxes are pretty well established as instruments, or they definitely influence alcohol use. And as far as I can tell, there's never been a study of alcohol taxes and dementia, which seems a little bit crazy. Like, why not do that? So I think there's a lot of potential, and certainly, yeah, there really are actually a lot that people are doing. So people are doing a fair number of things on policies that are around financial security. So EITC policies, not just education policies, but other kind of social security policies. So I think there is a fair amount around this in the social, kind of at the place where epi intersects with econ, those folks who are living at that intersection. In terms of drug use, I made this when aducanumab was first approved. I was like all in favor of having a staggered rollout so we could actually evaluate the effect of the drug. And I still really believe in this, but I do not see it happening anywhere. The reason that I was such a believer in the staggered rollout is it was obvious we were going to have a staggered rollout. It was just that, very often there are not enough of there's not enough of a resource for everyone to access it. So it would be really nice if in that setting we implemented or rolled it out in a way that we knew if it was harmful or helpful. And this seems like a perfect case where, any kind of large body could implement a randomized trial. I mean, I think a quasi, like something that looks like a stepped wedge design, basically, pretty straightforwardly. And I think one of the values of seeing IV and learning IV, which I wish more people learned IV in their kind of core training, is to understand that you can introduce very imperfect randomization and then use it to estimate causal effects. You don't have to have perfect adherence. You just need to you just need to have a random source of variation that influences the chance somebody's treated, but it can be quite imperfect and still you can learn the causal effect. And we could embed that in all kinds of settings, but as far as I know, that's not really being done. And it takes a level of organization that's not feasible. Time varying confounding. So it really depends on the exposure, whether or not you can certainly have IVs that address time varying exposures. It is much harder. I think that is.
Wait, sorry. I mean,
So
not everyone can see the questions. I'll just read
okay,
the question
sorry.
or you could read it too. But yeah, so again, it flows nicely with your last answer. So there are difficulties with applying instrumental variables to time varying treatments in the presence of time varying confounding. How does this fit in with dementia research?
Yeah, I think it totally depends on the exposure. So there are some there are methods. There's nothing intrinsic that IVs can't deal with time varying exposures. And if you have a time varying source instrument, you're in good shape. However, it's hard to find an instrument for one exposure at one time point to find an instrument that is an exposure at multiple time points. I do think there's some innovation around that, like I'll give an example that I think addresses this, which is in the MTO study, children were different ages at the time of randomization. And you can think of the age at which they were randomized as a whole other source of variation that is essentially influencing the duration of their exposure. So I think there are opportunities, but I totally agree with this point. It is an area where identifying instruments and figuring out how to actually use them is challenging. And there's some settings where you just flat out get the wrong answer if you're not attentive to the fact that, for example, there's crossover in treatment.
All right. And the next question is, how much do you worry about validity of dementia ascertainment? They find that with active surveillance, event rates can be vastly underestimated without active surveillance. Sorry.
Yeah. Yes, dementia ascertainment is so challenging. To tell you the truth, I really think we lean on dementia as a diagnosis too much as an outcome. And I think for dementia research, we are better served by at least complementing with longitudinal measures of cognitive change and cognitive loss. Because of this issue, because of the issue of confounding, and also because of the issue of underdiagnosis. But whether the underdiagnosis gives you the wrong answer or plausibly gives you the wrong answer really depends on the exposure, right? So it probably doesn't matter very much for genetic risk factors, right? It probably does matter a lot for something like education or a disease comorbidity that would directly influence the chance that you get diagnosed. And my student Jingshuan is doing a paper right now in UK Biobank where it's just sort of going through a few different reasons that you might get healthcare that, it's hard to find something that's definitely not associated, definitely doesn't influence dementia. But you can look at a few different reasons that don't seem so strongly. And you can also basically see the year after you get care for that thing, there's a huge spike in dementia diagnosis, and then it sort of attenuates over time. That's not true for every exposure. Like diabetes, you have elevated risk of dementia diagnosis right after your diabetes diagnosis, and it stays elevated. But many things like you come in for care and you have a very high risk right away, and then it kind of attenuates. And that to me seems like it's diagnostic bias, and it could be a big problem for lots of especially clinical questions.
We have a question from the dean. What factors can help substantiate the methodology, e.g. regional differences, evidence of genetic predisposition, generational or ecological disposition?
Yeah, I think, again, it really is dependent on the research question. What's going to be most convincing about varying them, to vary the method. So if you think about, I'm not sure that I'm totally understanding this, but I think what you're asking is like, what is the best way to triangulate? Like, how do you, so I think in each setting, you want to say, well, this is the evidence we have. What do I actually think is the most plausible alternative explanation? And then try to find a setting that will rule that out. And I think geographic heterogeneity, I think, is often very powerful. I have found the genetic variants to be useful for this reverse causation thing. I think that that is kind of helpful. Forward Mendelian randomization in some cases I think works. I will say that for social exposures, I'm very skeptical of Mendelian randomization, because I think it actually just exacerbates, like, I think it actually has all the biases of observational studies and then some. But I think that this question of really what is the most useful way to substantiate the methods depends on the substantive application.
How do researchers ensure transparency and rigor in the process of evidence triangulation?
We could have just stopped with rigor, like evidence. I think if you're trying to triangulate, it actually naturally leads to more transparency, because the essence of triangulation is to say, here's a weakness that makes me worried about my results. I think sometimes pre-registration can be helpful, but sometimes pre-registration is just, it's so hard to do effectively. One thing I think I'm sort of excited about right now, I don't know that this is the answer to this like very important and big question, but one thing I'm sort of excited about right now that we're starting to do in a couple of our studies is these vibration of effects studies. Like I think Chirag Patel has beautiful examples of this, and maybe champions this. The idea is to actually say, what are all the ways that you can do this, that you can specify this model? And for example, we're estimating the effect of statins on dementia incidence. So, and we're using a big healthcare data source, healthcare membership data source. And so we can have different exclusion criterions. We can have different run-in periods. We can exclude the people with MCI. We can have different outcome definitions. We can take outcome definitions that were from only outpatient or only primary care or only ones that were confirmed by specialty. All of these different variations. And once you start doing the combination, you very quickly have thousands of possibilities. And I think this aligns with, the idea of the garden of forking paths, like Gelman's garden of forking paths, where you have a million decisions. And by the end, if you always turn the direction that brings you towards statistical significance, you're going to get it after 1,000 decisions. But the idea of vibration of effects is you actually look at all of those, like you just loop your analysis over all of those decisions, and then you can see, is it really vulnerable to those decisions, or are you basically getting the same answer for across all of those decisions? I think that is very exciting, and it's something that you couldn't even have dreamed of doing 20 years ago because we just didn't, you couldn't do the computational power. But now it's feasible. It's often very feasible, and I think we can be a little bit more systematic about trying to do that.
I think Gelman calls that a multiverse analysis. Yeah,
Beautiful.
I have a couple of questions too. So you mentioned, IV and covariate adjustment methods and front door criterion as like 3 alternative strategies. How about parallel trends as another one? And then also, I know you work with Eric Chechen a bunch. Are you guys trying to come up with any proximal inference study designs that might work for dementia using negative controls?
I am not working on proximal inference, even though I think it's the coolest. I've gone to talks and been like, oh, awesome, Eric. And parallel trends designs, I would actually talk, when I say IV, I think of any exogenous source of variation in the exposure. And so I think parallel trends designs you could probably put under that bucket. Do you agree with that?
To me, they're different assumptions, because I mean, you don't need like the exclusion restriction or anything with parallel trends. often people invoke like some type of randomness as a justification for why you might expect parallel trends to hold, but even if there isn't randomness, like you could still have it.
So where would you think of this as a different category of causal inference?
Yeah, I think it would be like a different assumption that people commonly invoke, like in the health and retirement survey, maybe like you could just assume that the cognition scores would decline in parallel for people who either, let's say, retired or didn't retire. So, some life event went into poverty, didn't go into poverty, in the absence of going into poverty.
So one way is to think of yourself as your control, right? So that's one way to think of this. And so then you could put it under backdoor criterion where you can say, oh, we were actually controlling for you. You're like a fixed effect. And there are these designs that I'm like actually not sure. And I disagreed with people about where you should put them. And I don't know that it's necessarily essential, but I think there's a set of designs where you can think of like the what goes into your sufficient set, what it goes into your covariate set is basically a fixed effect that captures a whole bunch of unknown covariates.
Yeah. And then one more, could you expand a little bit on why you think the definition of triangulation should be like a little broader than like Lawler and Swanson and Lebrecht were saying?
Well, Lebrecht and Swanson were actually very narrow in that I think if you adopted them at face value, you couldn't use evidence triangulation to say it's a positive effect. And I think for many substantive questions, we actually don't really care that much about the point estimate. We really care that it's like harmful or beneficial, because we're not going to make a different decision if the hazard ratio is 1.6 or 1.8. It's like, we're going to make a different decision if it's 1.6 versus 0.6. And so I think that so that's one thing. The other thing I think is that I don't know how their tool or their framework fits onto bias assessment, like actually saying, I'm going to go over here in a whole different study. Like, you've said that you don't have an association between IQ and educational attainment, that's a key assumption for your study. I'm going to go over here in a whole different study and show whether IQ predicts educational attainment. To me, that's evidence triangulation, and I don't think it quite fits with what they're describing, which is not like what they're describing is very helpful and informative, but I just think it's narrower. And for us as a field, I think we're better off thinking more inclusively.
Okay. Any more questions in the chat? Speak now or forever hold your peace.
Oh, Rebecca has this great argument.
Oh, oops, I need to scroll down. Okay. So Rebecca said, I think magnitude almost always matters. We might need to make trade-offs about resource allocation depending on the magnitude of two positive effects.
I hear you, and I also think that's really idealistic about how policies get made. And like, we're almost never like, I think in a great world where we were really rational policymakers, that would be true. But I think, in fact, people, the big sausage machine that is between the evidence and what anybody actually does, whether that's a policymaker or an individual making a behavioral change, is very rarely really classifying in that way. And it's not that it's never, like, I agree in theory, like if you think about, the new Alzheimer's drugs are probably going to increase risk of hemorrhagic events. And we might really want to know what's the effect on hemorrhagic events that compared to the potential cognitive benefit. But I think in many, many settings, we're going to make a decision based on the sign of the effect. And we are just not in a position to use such precise information. But
says,
maybe someday we will be. Like, it would be great if we were. Okay.
Okay, going once, going twice. All right. Thank you very much. That was
Thank
great.
you. Thanks so much. Take care. Bye-bye.